All right, so we're looking at chapter 3.4, linear programming. Now, linear programming is used to optimize real-life problems. Now, optimization is the process of finding the maximum, the largest, or minimum, also known as the smallest, value of some quantity. Now, it's also the process of optimizing what we call a linear objective function. Now, that function is subject to a system of linear inequalities, which we call constraints. The graph of the system of constraints, the linear inequalities we just practiced doing in chapter 3.3, well, when we shade that part that's all in common, we call that the feasible region. Here's an example of the two different types of regions we can get. We have what's called the bounded region, which we did in the previous chapter, but also the unbounded region. I did one example like that, where it goes out to infinity and beyond. Now, in this first example, we're just going to go over how to do the concept, and we're going to build up to a real life situation. We're going to use the objective function to do these, but first we need to graph our constraints. And so we see here x greater than or equal to 0, y greater than or equal to 0 means we're dealing with just the first quadrant, and because they have the equal to signs in there, we don't really have to draw anything as we don't have to have dashed lines. So we just need to know that our x-axis and our y-axis act as boundaries. Alright, so then we have our last inequality there. It's written in a format that we can use our x and y intercepts. Very simple one there. X is going to be 8, setting y equal to 0, and y will be 8, setting x equal to 0. It's going to be a solid line connecting those two. And then if we were just to shift it over, if we need to do that, if you don't, that's fine. We're shading below the y-axis. The y-axis there is 8, and so that means everything below. And just make sure you don't go past the x and y axes. All right, and then you're done. Now that's what we do in inequalities, but now we need to find the minimum and maximum. When dealing with a linear programming question, we have to use the objective function to find our values. And the way that we do that is we substitute the vertices, the value of the vertices, into the objective function to find which value yields the minimum and the maximum value. So first thing we need to do is find all the vertices. The first one, and the vertices of the feasible region, the one that we just shaded. First one is going to be here. I'm just going to change the color. That's our first vertex, corner point. It's another way that you can think of it. One here and one here. So we have 3 corner points. And so just think of it as if this was a triangular table. We are the corner points of the table. Right? So whatever type of shape pops up, you're looking for the corner points. All right, so now we go ahead and substitute our values into here. We're going to use c equals to 3x plus 4y, and that's going to determine what is the max and the y, the max and the minimum. So we start off with the first point. You could use the 0, 0, just work your way around. X is 0, y is 8. And so we substitute that into the function to see which one is the max and which one is the min. So here we have c equals to 3 times the 0 plus 4 times 8. And since 3 times 0 is just 0, 4 times 8 is going to yield us an answer of 32. So we have 32 there. And then we can put in the next one, which would be 0, 0. We can already see there our value is just going to be 0. So 3 times 0 plus 4 times 0 is equal to 0. And then the last one is x is equal to 8, y is equal to 0. And we substitute into our objective function, so 3 times 8 plus 4 times 0. And so we see here 3 times 8 is 24. So now we need to pick our max and minimum. And so you can clearly see what that is, hopefully. Our max is going to be 32. And it's going to be 32 when x is 0 and y is 8. So 32. And normally you would say that. But I'm just going to put here max 32. Yeah, I'll just do that at 0, 8. And then, and don't use the at symbol. Then we have our minimum value is going to be 0 at 0, 0. All right, now that's important. So when we get to a real question, you state what the x is. If x was balloons, you say that we have a 32 max at when we use 0 balloons and like 8 birthday hats, right? This is just an example. Right, so that's how you do that. Very simple process. Just do the linear inequalities, find the corner points, substitute them into the objective function. All right, let's do another one. That one had a bounded region. This one has the unbounded region. And so we do the same thing. As you see, the constraints yield that we're in the first quadrant. Because they're greater than or equal to, less than or equal to, we don't have to draw in any lines. So we just have here our x-axis and our y-axis. And we can find our x-intercepts pretty quickly. Hopefully by now you could do them in your head. We have 3x is equal to 18 because we set y equal to 0. If we divide both sides by 3, x will be equal to 6. For our y-intercept, doing the same thing, setting the x equal to 0, it's going to leave us with 4y equals to 18. This won't divide as evenly, so we're going to have y is equal to 4 goes into 18 4 times with 2 left over, so 4 and a half. All right, so then we just go ahead and graph those. And so we have x equals 6. All right, we have our x equals 6. Just got to get control of the pen again. So x is equal to 6 and y equals to 4.5. That's going to be here. All right, and so we just need to connect that line there. And it's a solid line as we saw. And then it's greater than or equal to. And hopefully you can see by now if it's a positive y and then greater than or equal to, it just simply means everything above. And so all of this region would be shaded there. All right, and so any point that you choose there will work, but it's unbounded. There's nothing on the top to bound it. And so we call that an unbounded inequality system. All right, so now we need to go ahead and try to find the minimum and maximum value of this function. And so the way that we do that, remember, we're going to substitute our values, the intersections, into the function. This is slightly different from the one in the book. I had left out one of the inequalities. So we just work ahead with this one. But it's just simply our intersections there. And so we have one here and one there. So we're just going to substitute those two values in there. And what we'll see here is that we have the point x equals 6 and y 0. And then we have x is equal to 0 and y is equal to 4.5, 4.5. All right, remember we're going to substitute this into the function. And so we have here c is equal to 3x plus 4y. And so if we go ahead and solve those, we're going to have 3 times 6 plus 4 times y. 4 times 0. And 3 times 6 is 18. All right, so we get 18 for that first one. For our second one there, we're going to have 3 times 0 plus 4 times 4.5. 4 times 4 is 16, and half of that is 2, so we get 18 again. So we get two minimum values there. And the reason why we say minimum is if I was to choose any other value and try to use it, we see that it only increases. We don't have a maximum value because it's unbounded. There's no cap to this, and so we can only have a minimum value. And in this scenario, our case, our min would be 18. All right, so now we have an example, a real life situation. I took this from number 21. You can look over the example in the book to get a different variety of questions. Now the key here is to be able to pick out what is your objective function and then also what are your inequalities. All right, so the first thing you want to do is find out what your objective function is. And with the objective function, you can also find out what your x and y values are. I'm just writing this in shorthand for objective function. Now remember, the objective function is what you're maximizing. And so you're looking for something that is being maximized or minimized. This is really optimization. In this case, we're maximizing profit. So that means we're looking for a way to write the function based off of profit. Now the profit is written here, and we're doing 40 cents made on every gallon of berry fruity sold, and a profit of 50 cents made on every gallon of orangeade sold. And so we can see there that our profit margin, and we could use P there, is going to be based off of 50 cents times X plus 40 cents times Y. And I could rewrite that one to make it look a little neater. Alright, so now that I have my profit function, that's what I'm maximizing. I can use that to build up my inequalities. So I see here that I have X representing every gallon of orangeade. So that means X represents gallons of orangeade, and Y is going to represent gallons of berry fruity. And so we can now set up the rest of our inequalities, and I'll change them to a different color. So the first thing we want to know is that we're going to be in that we can't be less than 0 or equal to 0, right? So x has to be greater than or equal to 0 and y has to be greater than or equal to 0 because we don't want 0 gallons when we're maximizing profit. All right, so to do the next set of inequalities, we need to see what we are using to make the mixtures. And so we want to look at our orange juice. And we want to look at our, I think we're using, raspberry juice. All right, that way we can get the, I wish these little icons would disappear. That way we can get the rest of our inequalities. So how is our orange juice comprised of? Well, remember we got to split it up in terms of orangeade and berry fruity here. So our orangeade is X and our berry fruity is Y. So first we want to look at the orange juice that comes from the orange shade, or that will go into it. So the orange juice into let's change this color to, let's say, purple. So we're using 2.5 quarts of orange juice in our orangeade. So that means we have 2.5x. Then we're adding that on to the orange juice that's being used for our berry fruity, which is y. And so our orange juice there was what was it, 1 quart? I saw it somewhere. Okay, so let's read. Oh, they replaced it. They did it opposite. And so here we have 1x, or just, I'm sorry, 1y in terms of what's being used for our orange juice. And then the total amount of orange juice that we're using is 125. And the company has on hand, that means you're using less than or equal to 125 gallons. So that shows you the gallons of orange juice that's being used by mixture of orangeade and berry fruity. Then we could do the same thing and we could use green there. We're looking now at berry fruity based off of the raspberry juice used and also orangeade. So in the orangeade we use 1.5 quarts of raspberry juice. That goes second, I believe. Yeah, 1.5 was, oh sorry, that's on our orangeade, so that's 1.5x. Make sure that looks like a 5. Plus, how much raspberry juice do we use for berry fruity, which is y. 3 quarts of raspberry juice in our berry fruity. So that would be 3y. And the total amount of raspberry juice used, they have it mixed up a bit, is 150 gallons. So you got to be careful that you don't write it in the same order. So less than or equal to 150. All right, so I think that's the only thing we need. Right, we have our 4 inequalities. We know that our gallons have to be greater than or equal to 0. And then we have the orange juice and raspberry juice used broken up into the mixtures that they would be poured into. All right, so let's go ahead and see how many gallons that will be. So we already have our first quadrant. So that just means we need to figure out what our x and y intercepts will be. So let's just change it to purple. So for our x intercepts, and then our y intercepts. Okay, so then I'll put it in purple to represent orange juice. And so for OJ, we're going to have our x-intercept is 125 divided by 2.5. So just remember to write that in, right? So that's going to give us our x-intercept for OJ is x is going to be equal to 50. And our y-intercept for OJ is going to be y equals to 125, setting x equal to 0. Alright, so we could do the same for raspberry juice, and raspberry juice we put as green, so just put here RJ for raspberry juice. If we set y equal to 0, we have 150 divided by 1.5, and that's going to give us x is equal to 100. And then if we do 150, set our x equal to 0, we have 150 divided by 3, and though that's the easier one, we're going to have our y-intercept equals to 50. And I probably should have had a better graph. I'm just going to change that real fast. Okay, so we're going to go ahead and graph this. We're going to go by tens. We're going to change all of this to 50, and this is going to be 100, etc. This would be 150, that would be 120, etc. So everything's going by tens there. Just keep that in mind as we graph. So if you draw a graph of this, make sure you do that by tens. Alright, so here this is going to be 10, 20, 30, 40, 50, etc. And this is 10, 20, 30, 40, right up to 120. So let's start with our purple. We have there x is at 50 and y is at 125. So that represents our 125 on our y-axis. So to draw a straight line here, I just had to put in some points just to make it easier. But if you're using a ruler, that shouldn't be a problem. As drawing a straight line on here, I tried using a ruler, but that wasn't feasible. So I had to just go ahead and put those points in really fast. And so that would be our straight line, solid point through those dots. All right, so then we do the same thing for our next one. We have 150, so x at 100 would be x at 10, y at 50 would be y at 5, and we'll connect those ones as well. All right, so in the next equation, we are going to just connect those dots that have been placed in there for us. So we connect these with a straight line. I had to put those points in just to make it a little bit cleaner. Alright, so here we have two intersections. We have one intersection rather. And in order to continue this, we're going to actually have to work out what those values are. But before we do that, let's see where we're shading. We could use the double shade area. I'm going to see if you can follow along with the shading here. For the first one, we're shading in purple. And you see, because it's a positive y, we're going to be shading under the y-intercept. So we'll be shading all of this area, right? And that shouldn't go past the x-axis. Just keep that in mind. All right, so that shades all of here. And then for our green, if you were to change it to y-intercept form, you see it's a positive next to that y. So we're following that rule, less than or equal to. It would be everything under here. And so what we see that's in common is this region that I'm just going to reveal by erasing everything else. Right, so that's our region that's in common. All right, so to find our vertices, we have 1, 2, 3, 4 vertices. And so I'm going to have to clear all this stuff here, and then we can substitute our vertices into our objective function to see what the maximum profit would be. All right, so to make sure we had more room, I went ahead and put a computerized answer of our graph, or a computerized rendition of the graph. So here you can see it a little bit more accurate, as since I didn't have a ruler, it wasn't coming out as accurate as I wanted it to. But now that we've gone over how to graph it, and we went over the shaded region, we saw that the shaded region was here. And we see that we have these intersections and vertices. Now, you see that the first set of vertices are pretty easy to find, but this one is a little bit not as clear. If you had a really fine graph, you might be able to pinpoint where that is. Now, since we can't pinpoint it right here, and it's good that we go over this, what happens is if you get one that's a little bit off, you want accurate answers. So you're going to have to use some algebra, and that is the technique that we use when we run into any issue where we cannot determine clearly what the x and y is. And at this level, if you were hired to do something like this, they wouldn't want you to guess an answer either. And so in order to find this, we can use our understanding of linear systems. And because each of those lines represent a linear equation, we can do the what we learned, either the elimination method or substitution method for solving linear systems algebraically. All right, so what we can see there is that if we get our y's the same, we can eliminate them. And we could do that by multiplying the top row by -3. If we do that, we can rewrite our simultaneous equation, our linear system there, and we can go ahead and solve. So -3 times 2.5, and then 3 times the y, and then 3 times 125. All right, so we're going to have -7.5x plus -3y equals to just -375. All right, and then this one here can stay the same. And because the signs are opposite, we can just add them at each row together. And so -7.5 plus 1.5 is just going to take us to 6. And these will cancel. And so -375 plus -375 plus 150 is going to give us -225. And then we divide both sides by -6. And we'll get x is equal to 37.5. So that means our first x is 37.5. Then we just need to find the y value, and we can substitute our 37.5 back into the equation. Since this one, the first row doesn't have any coefficient next to the y, it will probably be our easier one. So we have 2.5x, which is 37 and 5/10, plus y equals to 125. All right, so we could go ahead and solve that. 2.5 times 37.5, and we get 93.75. And we can quickly find that subtracting the two values, and we get y is equal to 31.25. Now that's not an answer you want to guess at the Algebra 2 level. That's an answer that you want accurately. So 31.25. Now this will come in handy in our final answer. I'm going to erase this. You can always rewind it. Alright, so now that part has been erased, we can go ahead with our feasible region. Remember, we're going to be substituting each of those vertices into the objective function to see which one is going to be our min or max. Okay, so let's start writing out our vertices. Our first one, if we just went in a clockwise, counterclockwise, we would have x is 0. Alright, so we're going to substitute each of these in there and solve. And you can see this can be pretty long in doing these equations. So going ahead and we're going to substitute each one in there and see which one is our proper value. So we have our profit margin. It's going to be 0.5 times 0, which we know is 0, plus 0.44 times 50, 44 hundredths times 50. All right, so we want to see what that's going to be. You could use your calculator, or you could work it out by hand. 0, and we're just going to get the final answer there. So 0.44 times 50 is going to give us 22. So that's a profit of 22. We have 0, 0, so we know that's just going to be $0. And then the next one, we're going to have 50, 0.5, or half, 5/10 times 50, and we know this one's just 0. And so half of 50 is 25. So $25. And then the last one, we want to substitute that one in. We have P is equal to halves, 5/10 times 37.5 plus 44 hundredths times 31.25. we're going to get $32.50. Okay, so you can see what their profits are going to be. And I see a little slight mistake there. This should have been 0.40. So that'll change our answer slightly. Just the top answer and the bottom answer will be changed just slightly there. I want to make sure we have accurate answers. I wrote that down wrong when I typed it out. That should have been 0.40. All right, so we got a profit, $31.25. That's our max. And so you see why it's important to get the accurate amount, because if you were reporting your final data that's reported here would be, you want to use, I erased our axis, but if I go back, our axis, we were looking for gallons. And so our axis in terms of gallons, all right, so remember our X was gallons of orangeade, so I want to have 37.5 gallons of orangeade. I'm just going to put here capital O, and I want 31.25 gallons of, what was the other one? Berry fruity. So I'll just put here berry fruity. All right, so if I got 37.5 gallons of orangeade with 31 and 25 gallons of berry fruity, it'll give me a maximum profit of $31.25. So if I worked at a juice company, I could get this information and tell them their maximum profits based off of the different amount of gallons of the juice mixtures they make. All right, so that's you can see with practice this becomes easy. Remember, start with your profits, your maximizations rather, or minimization, which I'll just say optimization, and work your way to your inequalities, graph them, substitute them back into the objective function, and you can get your final answer.